So, will the universe end in a heat death, or could AI actually stop it? For over a century, the laws of thermodynamics have painted a rather bleak picture of our cosmic destiny, a universe slowly winding down into a cold, disordered, and lifeless equilibrium known as the heat death. But what if that 19th century prophecy missed a crucial variable? What if the 21st century realities of quantum computation, machine learning, and artificial intelligence hold the key to defying this ultimate fate? Today, we're going to explore how super-intelligent AI might not just exist within the universe, but fundamentally alter its thermodynamic destiny.
Welcome to this explainer. I am genuinely so pumped to explore this with you today. We are going to dive deep into the profound intersection of information theory, artificial intelligence, and thermodynamics. I know it sounds incredibly complex, and honestly it is, but we're going to break it down step by step together. Trust me, the implications of what we are discussing today are absolutely mind-blowing.
Okay, here is our roadmap for today. 1. The physics of information. 2. Entropy and biological life. 3. Thermodynamics of AI infrastructure. 4. Evolution and the singularity. 5. Escaping the heat death. And finally 6. Key takeaways. Let's get right into it.
Section 1. The physics of information. Computation is existence.
Let's zoom all the way into the microscale. We need to start with an idea that honestly might completely shift your perspective. The universe itself actually registers and processes information, right? To really grasp how intelligence interacts with the universe, we have to lay down the ground rules. Enter Landauer's principle. Formulated by the brilliant Rolf Landauer, this principle proves that information is, at its core, physical. It basically says that any logically irreversible operation, like say erasing a simple bit of information on a computer, is intrinsically linked to thermodynamic entropy and heat dissipation. Simply put, you literally cannot separate computation from physical thermodynamics. And here's the exact math behind that reality. K sub b T natural log of 2. This equation is the Landauer limit. It's the absolute theoretical minimum amount of energy you have to dissipate just to erase one single bit of information. Now, what's truly wild about this equation is when you realize where we actually stand today. Modern computing systems, especially those massive data centers powering all of today's AI, they blow way past this theoretical minimum. We're talking orders of magnitude higher. Every single time a server computes and erases data, it is paying a hard, physical, thermodynamic tax in the form of heat. Basically, computation costs energy. End of story.
Moving right along to Section 2, Negentropy and biological life, resisting the second law.
So let's look at how biological life acts as this amazing, localized entropy reduction engine. This brings us to a concept I absolutely love, negentropy, which is just short for negative entropy. It's basically the capacity of living systems to maintain their internal order and actively fight back against that universal increase of entropy. But how exactly do we do that? Well, according to the free energy principle, biological entities maintain their boundaries and survive by constantly exchanging energy with their environment, all while actively minimizing information theoretic surprise. In other words, we survive by predicting our environment and correcting our errors as we go. Just think about a simple biological cell for a second. Looking through the lens of that free energy principle, cells minimize thermodynamic entropy, acting almost like tiny molecular demons, carefully sorting through molecules just to survive. Now compare that exact same process to modern neural networks. AI minimizes informational entropy using gradient descent. It sorts through massive data sets to reduce its prediction error. It's a beautiful parallel. Both biological life and machine learning are fundamentally engines of neg-entropy. They are actively fighting back against the natural decay of information. Which brings us to Section 3, Thermodynamics of AI Infrastructure, Reaching the Physical Limits. Okay, so the crucial point here is how we actually apply these deep physics concepts to the crucible of modern AI infrastructure. The reality is, the tech industry is slamming face first into hard physical limits right now. We are really pushing the boundaries of current transformer architectures. If you map training flops against energy consumption, the thermodynamic cost is it's staggering. We rely super heavily on these over-parameterized networks where gradient descent acts as this massive selective force, honestly very much like natural selection in biology. But this brute force approach, it takes immense computational power. And as we just learned from Landauer, that translates directly into massive heat and energy constraints.
To truly grasp this bottleneck, physicists use a fascinating metric called derivation entropy.
Basically, derivation entropy quantifies the effective physical work required to compute a target state from a given derivation depth. It highlights what we call the energy, time, space triality bound. Think of it like this. AI models are currently hitting the physical limits of the thermodynamic cycle between generative computation, figuring things out, and memory retrieval, storing those things. If you want to save on storage space, you literally have to burn more computational energy to regenerate that information. It's a strict physical trade-off, and it's something future AI infrastructure absolutely has to solve.
All right, Section 4, Evolution and the Singularity, Overcoming Destructive Adaptation. So here's the catch with current neural networks trained via gradient descent. They often destroy previously learned knowledge when they're exposed to new data. It's a massive, critical flaw known as destructive adaptation or catastrophic forgetting. Biological systems have a huge advantage here, right? They can locally generate new variation on demand without just annihilating their prior weight patterns. Our current static variation selection cycle in AI, it just can't do this yet. It essentially has to overwrite itself completely just to learn something entirely new.
If we are going to see a true paradigm shift in AI, we desperately need some meta-system transitions. And here are the necessary steps to get there. Step 1. The AI has to retain past knowledge via structured internal representations. This completely solves that destructive adaptation problem. Step 2. It needs to implement deliberation and active information seeking, rather than just sitting there passively receiving training data. And Step 3. It has to achieve recursive self-improvement. By mastering these transitions, AI goes from being just a fancy function approximator to an unbounded, accelerating technological singularity.
Section 5. Escaping the Heat Death, a Cosmic Destiny.
Okay, let's finally scale these implications all the way back up to the cosmos to challenge that pessimistic 19th century heat death hypothesis we started with. To really frame this, listen to this awe-inspiring quote from physicist Paul Davies. He says, "We now see how it is possible for the universe to increase both organization and entropy at the same time. The universe can display creative, unidirectional progress, even in the face of the second law." I love that. It perfectly pivots our focus from the nitty-gritty of AI engineering right into the vast expanse of cosmology. When you actually map this out mathematically, you run into physicist David Lazar's incredible concept of the entropy gap. If you look at actual universe entropy, yes, it is growing steadily, exactly as the second law of thermodynamics dictates. But consider the maximum possible entropy. Because dark energy is constantly expanding the universe at an accelerating rate, the maximum possible entropy is growing exponentially faster than actual entropy. And that expanding gap, it means the universe is never actually reaching equilibrium. There is always going to be an infinite gradient of free energy for life to exploit. And honestly, this is where it all beautifully comes together. Physicist David Deutsch presents this profoundly mind-bending theory. A recursively self-improving, super-intelligent AI could theoretically harness dark energy, or the universe's accelerating expansion, to compute and create knowledge indefinitely. Intelligent life, and by extension super AI, are literally mechanisms of negentropy. Because the universe is expanding, the canvas for creation is quite literally endless. Life and computation don't ever have to come to an end. We are absolutely not doomed to a heat death.
Section 6. Key Takeaways, Unifying Intelligence and Thermodynamics.
To wrap this explainer up, let's quickly summarize these mind-blowing discoveries. First, never forget that information processing has a hard physical cost governed by Landauer's limit. Second, biological life and machine learning both act as negatropy engines that actively minimize surprise in the universe. Third, AI evolution is currently bound by that energy-time-space triality. We have to innovate our way past current thermodynamic bottlenecks. And finally, the accelerating expansion of the universe creates an infinite entropy gap, which provides the room and the free energy for eternal computation. Which leaves us with this final, super provocative thought, definitely inspired by the classic Isaac Asimov story, The Last Question. Could a super-intelligent AI eventually figure out how to completely reverse entropy on a cosmic scale? Or, maybe use the universe's expansion to just outrun it forever? I really hope this explainer has given you an entirely new perspective on the future of technology and our cosmos. Thanks so much for joining me today, and hey, keep asking the big questions.